Okay, with our last lesson, we're going to look at how to do an analysis of that does comparison of three or more means. We've talked about how do we do a test of hypothesis regarding one mean of a population or one population mean, how to do a test involving two population means, both with independent samples and dependent samples. Now we're going to talk about what happens if we have three or more populations and we want to compare their means. And in this case, we're going to restrict our attention to independent populations. We're going to handle this by doing what's called a one-way analysis of variance. Analysis of variance is often shortened to the word ANOVA, A-N-O-V-A. So what we're going to talk about in this chapter is what are the requirements to perform an analysis of variance, and how do we conduct a test of hypothesis regarding three or more means using one-way ANOVA. So analysis of variance, or ANOVA, is an inferential method used to test the equality of three or more population means. One note of caution: the reason that we want to use analysis of variance when we have three or more means, rather than doing pairwise comparisons, is that if we were to use pairwise comparisons, each one of those would be subject to a type 1 error of alpha. By combining all of the tests together, we end up with a type 1 error that's much higher than alpha. For example, let's say that I have, as an illustration, I have a 5% chance of making an error on one test for each time I run the test. Well, if I run that test 20 times, I'm almost certain that at least that one of those or more has had an error in it. The more times I conduct a test, the more likely I am to have made a type 1 error. So I would like to come up with a way of conducting a single test so that I only have to worry about having a mistake one in alpha alpha percent of the time. There are some requirements that we have to perform analysis of variance. One, for each of the k populations that we're going to test, we need to have k random samples. The samples have to be independent of each other. We're going to use the same underlying assumption we've been using on all of our other tests, that the underlying populations are normally distributed. And the one new restriction we're going to have is we're going to make the assumption that the populations have the same variance. So each treatment group in the population has variance sigma squared. Kind of a picture of what we're trying to do. Our null hypothesis is that the multiple means that we have are all the same mean. That would be this first picture, where the means of all three populations are equal to each other, so I get the same distribution. The alternative is at least one mean is different from the others. Means I could have a number of different distributions. They all have the same shape, but they're not necessarily centered at the same point. The methods for ANOVA are robust, so small departures from normality are not significantly affected in the results. In addition, the requirement of equal population variances did not need to be strictly adhered to, especially the sample size for each treatment group is the same. Therefore, it is worthwhile to design an experiment in which the sample sizes from the populations are roughly equal in size. One way for us to somewhat verify that the population variances are about equal is if the largest sample standard deviation is no more than twice the smallest sample standard deviation. If that's the case, then one-way ANOVA is usually going to be pretty appropriate. We'll talk about some other tests that you can run as well in that situation. There'll be things that will be done completely numerically just to try to check the assumption. So let's take an example to verify. Let's say we had the weight in grams of pennies minted at the Denver Mint in 1990, 95, and 2000. We want to verify the requirements in order to perform a one-way analysis of variance. So we have these samples. Looks like I think we have 11 or 12 pennies in each one. I think 11 pennies in each sample. The samples are paid independently. I randomly pick the 11 pennies from each one. You can do a normal probability plot to make sure that they're roughly normal, and that's pictures that look like this. Again, for our class, we're going to assume that we've already checked this and that the normality is satisfied. You can calculate the standard deviation for each one and verify that twice the smallest is less than the largest standard deviation. And so again, if you look at what the number, there's 11 pennies in each one. Here's the average weight for each of them. Here's the standard deviation. We can verify that the largest sample standard deviation is less than 2 times the smallest standard deviation. Now we're going to start talking about how can I construct a one-way analysis of variance. And in doing the one-way analysis of variance, we're going to use something called the F distribution. The F distribution is similar to what we've been dealing with chi-squared tables and normal tables and t-tables. It's just a distribution that describes a certain set of events. It is more difficult to generate a table for the F distribution. So when we're doing analysis of variance, we're going to restrict our attention to just the p-value approach. And the idea behind analysis of variance is to compare how much variability there is within each sample to the variability between samples. Let me give you an example. Let's say that we have a dartboard, and I have 3 players. Player 1 throws 3 darts. Player 2 throws 3 darts. And player 3 throws 3 darts. Okay. Now let's take the same setup on another dartboard, and we have 3 players there, and player 1 throws 3 darts, and player 2 throws 3 darts, and player 3 throws 3 darts. And I step away for a minute, and I come back, and another dart has been thrown on both boards. By looking at the 2 dartboards, can you tell me who threw the dart? Well, looking at this dartboard, there's so much variability so much variability of each player's shots that it's very difficult to distinguish between each player. So when I see this green dot or this new dart thrown, I really don't know who threw it because there's no way for me to distinguish between the 3 players. there's a lot of variability within the throws for each player, so it's hard for me to distinguish in the variability between the players. However, on the second one, each player is much more consistent with where they're throwing. There's much less variability within the patterns for each player. So the variability between the players is much more evident. So based off of this, I can look at, oh, this green one is very close to these yellow dots and far away from blue and red, so it's very likely that it came from the player who threw the yellow darts, or the one that's marked by yellow points on my picture here. So the idea of analysis of variance is to compare how much variability there was within each group. So how much variability is there within the darts that each player threw, as compared to the variability between the dart patterns. So if the distance between players is greater than the distance within the throwing pattern of each one, I can tell that the means are different from each other. If the variability within each player's throwing pattern is the same or more than the variability between, it's hard for me to distinguish. So the idea of analysis of variance is to try to measure how much variability is there within each column of numbers or within each player's pattern, and how much variability is there between the averages, and compare to come up with if that difference is big or small. So some places where analysis of variance might be appropriate would be a researcher wants to compare 3 different methods for teaching reading. I have a reading score that I can evaluate the reading capabilities. I can take my groups and split them up into 3 different groups. Each group will get a different methodology for teaching reading, and then I can compare their average reading scores at the end of the experiment to see which one has a better reading score, or if there's any difference between them. The null hypothesis with analysis of variance is that none of the teaching methods would be preferred over the others. They would all be equally effective. The alternative is that at least 2 of the methods would have different scores. Another alternative, or another example, would be measuring the effectiveness of weight loss programs. And maybe there are 4 different weight programs I'm interested in studying. I can place my participants randomly into each of the 4 groups. I can then look at the average weight loss that they have and compare the average weight losses between each group. So for an analysis of variance, we're assuming that we have equal means. That's always the null hypothesis here. It's still an equality statement. And we're assuming that we have equal means. The alternative is that at least 2 of the population means are different. The test statistic that we're going to calculate is an F test statistic that goes with the F distribution. It's given by the equation S sub b squared over S sub w squared, where S sub b squared represents the variance between columns, and S sub w is variance within columns. So you can think about, in our DART example, S sub w squared would be the variance within each one of these patterns, yellow, blue, and red. The variance between would be the variability between the averages for each of these 3 columns. or these three groupings. We're not going to worry about the degrees of freedom and everything. It does illustrate why we're not that interested in putting together a table for us to look at, is that we now have three things that our table is going to depend on, and so it becomes a much more complicated situation. We want to concentrate on what's the test statistic measuring, and how can we then, given some information from a statistical package, interpret our results and go from there. Again, the assumptions are that the underlying populations are normal, the variances are equal, and that each of our samples is randomly selected from the K populations and independent of each other. So let's look at a specific example to try to illustrate the logic. And so this will be a numerical example similar to the DART example, but it will put it in a hopefully a better context. So let's suppose that we're interested in comparing the average yield per acre in tons of three varieties of apples, where we take samples of 5 acres selected from each orchard. So each one of these values would be the number of tons of apples obtained from each one of the 5 acres. So this 5.9 is 5.9 tons from the first acre, and we have 5.92 tons from the second acre, 5.91 tons from the third acre, and so on. And we're going to do that in each of our 3 orchards. Overall, I can look at, here I had an average yield of about 5.9 tons for this first orchard or first variety. I have 5.5 ton average for this second variety, and a 5 ton average for the third variety. Notice that within each one of these columns, the numbers are grouped very close together. And that holds true for each one of the 3 columns. So this is kind of like the second dartboard that we showed, where the groupings were very tight together. So when I look at the difference between the averages, between the columns, this seems like a much larger or a much more significant difference because the variability within each column is so small. So based off of the idea that these do not vary much within columns, and I get an average of 5.9 here and an average of 5.5 there, it is reasonable to assume or to conclude that these 2 averages are not equal, that the 2 varieties are not going to produce the same yield. But what if we have a little bit different set of numbers? Same concept. We're going to take our samples of 5 acres and look at the tonnage that comes off of those 5 acres. And we get 5.9 tons in the first acre for sample 1, and 4.42 in the second acre, and 7.51 in the third acre, and so on. I still have the same averages overall, but now the variability within this column is much greater than it was before. A difference of 50 cents does not seem, or 0.5 tons, does not seem like nearly as significant of a difference because the spread of the numbers here is so much greater, right? We have a range of $3.50 or actually $4 here between the low and the high. So a change of 50 cents between these averages doesn't seem significant. This has a very small within variability compared to the between variability. Here, my within variability is large compared to my between variability, and therefore we cannot distinguish between them. So this is like the first DART picture that we showed, where everything was scattered all over the board. So I want to go through this second set of numbers and show you how we would calculate S sub within squared and S sub b squared. This is a slightly different method than what the textbook uses, This method that we utilize will result in the same values, but is a little bit easier to follow. We have our data organized into columns here. Each one of those columns will have its own average and its own standard deviation. Remember that standard deviation squared is the variance, so each column has its own average and its own variance. We want to come up with the within variance. Well, under the assumption that the underlying population averages are all the same, and the standard deviation and the variances are all the same, each one of these sample standard deviations from each of the three columns is an estimate of the underlying population standard deviation or underlying population variance. So I can get an overall estimate of population variance by taking the average of these three things. Each one of these values gives me an estimate of the variability within a column. So if I take the average of those variabilities, I get an overall estimate of the variability within a column. Now, to get the overall average, or get the variability between columns, I need the overall average. If I were to take the overall average of all 15 of these values, we would get an overall average of 5.47. I could then come up with the variability between columns by looking at the variance of these three average values about the overall average. So we'll go all the way back to what we did at the very beginning of the semester of taking each value we observed minus the overall average and squaring it. So we're going to come up with the sum of the squared deviations, and we're going to divide by n minus 1. So this gives me a variability between columns, but that's really kind of only for one set of observations. So to get the overall between variability, I need to multiply by the number of observations that I have. So it's n times this s sub x bar squared. Remember that these are sample standard deviations, and the sample standard deviations follow a distribution that is the population standard deviation divided by the square root of n. Solving that backwards gives me this equation. So the between variance is n times s sub x bar squared, which gives me 1.0167. So my test statistic would be 1.0167 over 2.33, which is 0.436. Turns out that this is a very small value. It's not going to be significant. As we kind of surmise just by inspection, it's not going to be possible for us to tell the difference between these values. So let's do this example in StatCrunch. And from that, see if we can see where some of these numbers come from. Again, on the final exam, I'm not going to expect you to go through the whole process that I have here of calculating the standard deviations and the averages, or the variances and the averages. I will most likely give you each of these values, and then you would have to calculate, but most likely I will give you these values of averages. I'll give you the overall standard deviations, and then I will most likely ask you to find the within variance. I'll probably give you s sub x squared as well, and have you find the between variance, and then calculate the f statistic. I am not going to have you go through the entire process of calculating the averages and standard deviations, or the averages and the variances. Okay, so let's look at our StatCrunch example here. And I am going to take these values and I'm going to copy them over to StatCrunch. So we get that. And I'm now going to go to Statistics, Analysis of Variance, One Way, and I want to select the 3 columns, and I'm going to hit Compute. Notice that the values that I get for my averages are the average means that I have here. I see the standard deviations, which you'll notice comes up with the values that are in the standard deviation row. I also get the F statistics that's showing up here. You'll notice that the mean, the MS column for columns, matches up with my between variability. This is called the mean square error between the columns. So we have the mean square of the columns. This is S sub B squared. And then I have the within variance, that is my mean square error. It's the standard, or the variability between or within each column. So this is my within variance. This is my between variance. I can take the between variance divided by the within variance, and I come up with this F statistic. Now notice that there is a p-value of 0.6565. This p-value is very similar to what we did previously, in that it would need to be less than our alpha level that we would select to be significant. So because this is much greater than pretty much anything we would pick, there's not sufficient evidence to say the means are different. So now let's go back to that set of data that we had originally and copy it over to StatCrunch. And do stat, analysis of variance, one way. And we're going to do 5, 6, and 7. And to highlight more than one column, I had to hold down the Shift key and hit Compute. Again, I can see the same means and standard deviations as were calculated, or means before, then standard deviations are now there. But you can also see that the F statistic is very large with a p-value that is very small. And so we have very strong evidence that the means here are different than from each other. The variability within each column was very small compared to the variability between the columns. The further F is away from one, or the larger F is, the more the between variance is outweighing the within variance, and the more likely we are then to believe that the means are different. Well, once we have the means being different, how do we analyze which ones might be different? And again, we want to try to do this all with a single test. So in working with the analysis of variance, there's something called Tukey's method. That I can click in here in StatCrunch that will compute. And what that does is it creates the analysis of variance and shows me my probability. but it also shows me some confidence intervals for the differences between the various means. If the confidence interval contains 0, then I cannot conclude that the means are different. If the confidence interval does not contain 0, I can conclude that those two means are different from each other. If the confidence interval contains 0, then I cannot say they're different from each other. So in this case, this confidence interval does not contain 0, so that tells me that what we had in column 5 was different than what we had in column 6. The average from column 5 is different than the average from column 6. In a similar fashion, this interval does not contain 0, so I can say that the average for column 5 was different than the average for column 7. And here, I can say that the average for column 6 is different from the average from column 7 because this does not contain 0. If I do it with the original, or with this first set of data that I've copied over here, so the first 3 columns, and I run Tukey's comparison with it, then looking at the confidence intervals that come out there, notice that this confidence interval contains 0. So there's no way for me to tell a difference between column 1 and column 2. If I look at this confidence interval, it contains 0. There's no way for me to tell a difference between column 1 and column 3. This confidence interval contains 0, so there's no way for me to tell a difference between column 2 and column 3. The way that the Tukey's comparison is set up, the overall error rate in the test is alpha. So by doing these comparisons in this manner, we're able to limit the type 1 error that we would run into. I'll do some more examples in the next video, looking at both calculating the test statistic from some given information and interpreting Tukey's result and showing you how you can again do some things in StatCrunch to do the analysis for you. But this concludes our discussion of Chapter 13.